Hello, everybody, and today's World Quantum Day, by the way.
Oh.
Yes, there you go. Okay, so in a previous talk, we talked about this paper by Aronson and Gottesman, where they described improved simulation of stabilizer circuits. And so anyway, will you be, you can check if there are questions?
Yeah, sure.
Okay, I mean,
Go on Zoom, right?
yeah.
Okay, so
Okay, yeah.
questions I will
Just periodically, yeah. Okay, and so Aronson and Gottesman, and so one of the things that they looked at were the possibility of simulating circuits beyond just stabilizer circuits, which included non-stabilizer states. So what they found was that if you consider certain kinds of states where it's products of B-qubit systems, then you have a runtime that goes like, and D measurements goes exponential 2 to the 2B plus 2D times polynomial in the number of qubits. Or you could have non-Clifford gates, in which case you had a runtime that was exponential in the number of gates. Something like this. So in this paper, Bravyi and Smith and Smolin discuss an improved version of that by looking at Pauli-based computations. So what do they do? So I'm just going to give a broad overview. First, define the notion of a Pauli-based computation. Second, they introduced the notion of a stabilizer rank, which informally is basically you want to look at the stabilizer states as an over complete basis in your Hilbert space, and you can expand any magic state in terms of, or any state in terms of those stabilizer states. So the minimum such number of terms that you have in this expansion is known as the stabilizer rank. So they will define this notion of a stabilizer rank. They will compute a particular stabilizer rank for a particular magic state and show how that leads to, and so I can actually say this here. So kind of what they do is they convert the circuit-based model to a Pauli-based computation, which includes some magic states. So they convert it, and then they use the stabilizer rank to improve on the classical simulation. In particular, they will give something that's of order 2 to the alpha m poly n. I mean, this is probably the major result in my opinion. So we will work towards this, and then we will also describe some other kinds of simulations, namely, if you only have a quantum computer with n qubits, can you simulate something with more qubits? That's possible. You just have to run the quantum computer some number of times, and we'll also discuss that. So I'm partially worried that the microphone will be turn off. So, okay.
I can go get my earphone.
No, I think it's fine. I will just check periodically. Although it seems that there's, um, one moment, I will, it seems that it's not really easy to see what's going on. I will switch to my data. On here, it's quite blurry. So I'm saying I think that my computer is probably the problem. It's connected to the BilQC. So I will. Anyway, let's see what happens.
Yeah, whatever works, but here on my computer I see everything fine.
Okay. Let's see how it goes. Uh-huh. Let's see. Okay, so okay, so poly-based computation is the following. So just to remind you, we're going to consider polys. So let script Pn be be all Hermitian polys. And we know what a poly is. It's going to be something like where each I is taken from, so this could be plus or minus I, X, Y, Z. Okay, and then how does the poly-based computation go? Basically, the only thing that you're doing is poly measurements, but they could be acting on quantum states that are not necessarily stabilizer. They could be magic states. So we initialize each qubit in the state the magic state cosine pi over 8, 0 plus sine pi over 8, 1. And we allow a couple of things. So let me see if this is better. Yes, okay. So it proceeds by doing a sequence. So take a sequence of outcomes sigma 1 to sigma t for some polys pt in our Hermitian polys. This, by the way, a couple of things. The choice of PT is adaptive. And we also allow, so also these eigenvalues, the outcomes of the measurements, sigma I, or let's call it sigma T, are stored in classical memory. And also we allow Pauli and classical processing. Okay. Actually, I can put this over here. So we have this theorem. I guess I will number it. It's theorem 2 in the paper. Any quantum computation in the circuit model with n qubits and Pauli n gates drawn from the Clifford+T set can be a Pauli-based computation on m qubits where m is the number of T gates. Let's see if I got this. And also plus classical, plus Pauli and classical processing. Okay, very good. So let's think about how this works. So let me draw a schematic of how this is proved. So a little. The sketch goes as follows. So if you have a circuit-based model, we initialize everything in the all n qubits in the 0 state, and then you have a unitary which is drawn from Clifford+T. So maybe just to make clear that this is a unitary Clifford+T. And then at the output of the circuit, you measure each qubit in the computational basis, 1 to n. So this can be the same thing as, so we've talked about this notion of magic state simulation, which basically means that I take, for each T gate, I put a magic state. So if there's m of them, I do something like this. And now, instead of this being, instead of the unitaries being Clifford+T, I've replaced all the T's with a magic state. So I have a circuit that's drawn only from Clifford unitaries. But I can also do some measurements on it. I suppose I didn't use the same measure notation before. These are computational basis. And we do some computational basis measurements. This is one step. I've just inserted this T-state gadget everywhere, which I will explain in more detail just to remind everybody. What I can do is I can actually look at all of these measurements that are done in this circuit, and I can commute all the Paulis, all the Cliffords through, which just changes which measurements. But there are some Pauli measurements inside of this circuit as well, so maybe I should say that. So these are Pauli measurements plus Clifford So I will commute all of the Clifford unitaries through. That just changes which polys that I measure. So I have that this is something like and I just have some set of polys in here. So now I just have a measurement of a different set of polys. I can play a little trick here. So there's an additional sort of statement that comes that says that all of these, without loss of generality, all of these polys can actually commute, pairwise commute with each other. So we'll go into that argument in a second. But what that means is that I can play this trick. The trick is as follows. I can prepend a set of measurements after this, this zero state. And I can prepend a set of computational basis measurements here. And because of this earlier sort of result, more or less, that all of these measurements can be pairwise commuting, it means that all of these measurements will have to be pairwise commuting with these, right? Computational basis measurements acting on an input state of 0 will just give a trivial result. So this, I basically didn't do anything here, but because of this result that they can all, that without loss of generality, they can all pairwise commute, that means I can change again the set of polys that I measure. And I just need to change to a set of polys which, in effect, will not change what happens on this register. So in essence, I can just get rid of that register, and I'm left with just a poly-based computation, an input state of H. So I erased it, but a poly-based computation initializes in n, or m in this case, qubits in the H state. So basically, I will have reduced the whole problem to this. So let's sort of go and do that in slightly more detail. Whatever. Maybe I should have gone over there. Okay, so let's consider the following situation. So let U be a quantum circuit on n qubits with m T gates. Okay, so what we will do is we will replace each of these T gates with the following gadget. So what does that look like? Recall that we have something, because it's so last time we talked about a similar gadget, but we corrected the outcome of the whole gadget by a Clifford unitary. Instead, now we will just sort of, let's see how this works. It's slightly different than the scheme that I wrote down last time. So say you have some input state psi, and you have, it could be T or it could be H. So T, just to recall, is, I think it's like HS up to some proportionality. It goes like HS times H. It's something along these lines. So I measure This is on one qubit, this is on a second qubit. I measure ZZ Pauli, and then I measure X on the second qubit. And what happens is we get the following outputs. If I get, so say that this is some sigma ZZ, or just make it easier, sigma 1. The output of this measurement is sigma 2. So if they're both plus, then the output of the circuit will be T psi. If it's plus minus, it will be ZT psi. If it's minus plus, it's T inverse psi. And if it's minus minus, it's ZT inverse psi. And we can fix these in the following way. So we want to apply the T gate. So just here, if we have plus plus, we just don't need to apply anything at all. If we have plus minus, what do we need to apply? We can apply Z on the, this is just a single qubit. So we can just apply Z, and that gets rid of that one, minus plus. Because this is, if you remember the T gate, it's on the diagonal 1 and e to the I pi over 4. The inverse is minus I pi over 4. The way to fix this is to apply a phase gate, which applies a pi over 2, which fixes it. And then minus minus, you can apply, I suppose, S and then Z and then S, sorry, the other way. So everywhere that there's a T gate, we will replace it with this gadget, which includes Pauli measurements and some Clifford unitaries, which help to correct. So the next step we will have after we gadgetize the circuit, it's we say that let's call U prime the unitary after I will say replacing T states. So this is the gadget for the actual gate. So call this the new unitary, which we get by doing that replacement. And then we will, the next thing, sorry, I should have, I suppose, let's see, did I make this absolutely clear? No, I did not say this. Sorry. So in the first step, sorry, let me just write this. I forgot to say this. We initialize oh, okay. No, it's okay. So this unitary is acting on what? We have an initial state that's as follows. The initial state will be the n original qubits, and then either t to the m or h to the m. Yes, t to the m is fine. Okay, so we have this initial, sorry, I did it a little bit in reverse. So this is, we replace all the t gates with these t states. So now I start with a computation. We're going to start with a poly-based computation on n plus m qubits. That's essentially what we're doing. And then there's a unitary that's being applied. So the next thing that we will do, commute all Cliffords. So all that this does is inside of all of these gadgets, there are different polys and then different Cliffords. I'm going to commute all of those Cliffords through. And all of this does is it leads to different polys being measured. And then once you commute all of the Cliffords through and you update the polys, then you have the first leg of this, which is the following, that PBC on n plus m qubits on n plus m qubits simulates a circuit on, I guess, it simulates u 0 to the n. Yes, because this is u is the original unitary that we're applying. So we have the first leg of this. And now we want to show that actually these extra n qubits are unnecessary. There's a question. Slightly bigger. Okay, yes. Okay, slightly bigger, I will write. Okay, so now what we want to do is we want to show that extra n qubits are unneeded. Okay, so how can we do this? So first, the following. So in our poly-based computation, we have a sequence of polys, P1 to PT, with outcomes sigma 1 to sigma t. Say that for some PT plus 1, that it anti-commutes with one of the previous ones, s less than or equal to t. So one of the previous ones, so a PS is inside of here. Suppose that that was the case. We know that because this PS was measured initially, say that our state after t steps was phi t. Then what we know is that because we applied a sequence of projectors on our initial state, that it means that PS times, this is a quantum state, right? I'm just writing it without the ket notation. PS t is equal to sigma s phi t. And so when I apply the projector for this one, 1/2 I plus sigma t plus 1 pt plus 1 on phi t. I will use this relationship, 1/2 sigma s ps plus sigma t pt is acting on phi t. It turns out, and you can show yourself that this that there are well-known examples of this, that the sum of two anti-commuting polys is in fact proportional to a Clifford. So we have that. So for example, we have that there is some G element of Clifford n such that G is equal to 1 over the square root of PS plus PT, where these anti-commute. So just to give an example, the Hadamard gate is 1 over the square root of 2 x plus z, for example. So what is the sort of upshot of this? What it says is that when I measure pt plus 1, which anticommutes with the previous ones, I will get a random outcome with 50% probability. What that turns out to be is the same thing as applying a Clifford, one of these Cliffords with 50% probability. So what I can just do instead is say that I had a Clifford in my gate, and then I can commute that Clifford to the end of the circuit and update the polys accordingly. So essentially, once I implement a poly that anti-commutes with one of this set, that's like randomly applying one of two unitaries and then Clifford unitaries, and then I can just commute that Clifford unitary to the end, updating polys accordingly. So I'm just back to so without loss of generality, we can consider commuting polys, P1 to PT, all pairwise commuting. Okay, so now this is where you can get to a trick. I will introduce that picture again. So I had essentially something that looks like this, 0 to the n, t to the m, so some tensor product, and then I am measuring some set of polys. I can, without changing this circuit at all, prepend this set of polys with another set. This is the same exact thing as performing computational basis measurements here. I can do this, no problem. I didn't change anything. But now, because of this fact, or this basic idea that we can, without loss of generality, just consider pairwise commuting, now I've introduced this. That means that the operators that I choose here must pairwise commute with these. And if they pairwise commute, it means that they don't disturb this initial register at all, which implies that I don't need this initial register at all. So I can just, this is equivalent to just t to the m and some polys. And that actually, and that proves it. So that's the proof of theorem 2, which, just to remind you, was just saying that we can take any quantum circuit on n qubits and essentially convert it to a Pauli-based computation on m qubits, where m is the number of T gates. Okay. Hopefully the writing is a bit more legible now. So these are some, we want to prove theorem 4. But before I state what it is, let's just introduce some other ideas. So the basic idea is that Pauli-based computation can be simulated more efficiently than expected. Okay, so naively, what would you expect to be able to do? Naively, what you would expect is that first you have some quantum state to the 2n. You measure. So you measure a Pauli on this state so that you update it to phi t plus 1 equals 1/2 I plus sigma t plus 1 pt over 2. And this operation here, because you're dealing with matrix multiplications, and when you apply Paulis, this is up to phase factors. These are permutations. So this is order of 2 to the n. Sort of operations that you need for this one. So you can go ahead and, after some steps, this sort of naive algorithm where you can then talk about, okay, what is the outcome of this, compute inner products, and then flip a biased coin. But the net output is that there's this sort of naive thing that you could follow for Pauli-based computation, and it would go something like this many operations. So let's see if we can do better. So definition, the stabilizer rank of some Hilbert space is defined as the smallest integer chi such that smallest integer chi such that psi, the corresponding ket notation now, equals alpha equals 1 to chi C alpha. C alphas are complex coefficients, and phi alpha are stabilizer states. So maybe I just... Okay, so just a couple of remarks. One, clearly we should have that the stabilizer rank is between 1 and 2 to the n. 2 to the n is the dimension of my Hilbert space. So clearly, I should be able to express, if this is to be useful at all, it's got to be between these two numbers. And so also, let's just some notation. We're going to call chi n is defined as, as chi of h to the n. So we define chi n to be the stabilizer rank of n tensor factors of the magic state. And I wrote that down before. So okay, so just a couple of, let's see, maybe actually I can fit it in here so I don't have to. So there's a property, the stabilizer rank, which I'll abbreviate as SR, is submultiplicative. What does that mean? It means that chi of n plus m. What is this? This is the stabilizer rank when I have h as a tensor factor of n plus m terms, or n plus m factors. This has to be less than or equal to chi n times chi m. Why is this? Because we have that the tensor product of stabilizers are against stabilizers. So if I have that chi has some state h has a expansion with chi n terms, and another one has chi m terms. When I do the tensor product of them, I have at most that many terms, right? But it could actually be less. And so let's see an example. We already know that chi of 1 is equal to 2. I need the 0 state and the 1 state for this to work. It turns out that chi 2 actually is also equal to 2. For example, you can write out h squared as being equal to 1/2 times a Bell state, 0, 0, plus 1, 1, plus 1 over 2 square root of 2 times 0 plus 1 minus. This is just the Bell state with the second qubit being acted on by a Hadamard. So apparently, I didn't check this, that this is the smallest decomposition. You can have it be 2 terms. So now let's write down what theorem 4 is. Okay. Any Pauli-based computation on n qubits can be simulated classically in time 2 to the alpha n poly n, where you have that alpha is like 0.94. So okay, I guess it's legible. Okay, so what we want to do is compute the following quantity. We have a sequence of polys, and so the projection onto the joint eigenspace will be given by pi. So we want to be able to compute this. Say I have two quantum states, psi and phi, pure states. I want to compute this inner product, and then we'll take it from there. So there's a couple of things that we need to introduce. First, just for completeness, we have that f is a function from z2 to n to z8 is a degree 2 polynomial. Degree 2 polynomial if x1 to xn, these are each of the bits, equals f0 plus 2a equals 1 to n fa x a plus 4 sum 1 . So what are these coefficients? We have that this is in Z8. We have that these coefficients FA are in Z4, and these are in Z2. So also we want to use the following thing, that we have this fact, which I will not prove. If you want the proof, it's in Van den Nest 2011. And it's the following. Any phi element of the stabilizer, any stabilizer can be written in the following way. I should use psi. Can be written as some u element of z2n omega f of u okay, so let's unpack this just a little bit. This f is a degree 2 polynomial. This is a bit string on n elements. We have that this is a binary matrix on, so this is an element of Z. I'm trying to remember what they're called the dimensions, K cross N, so that this is a bit string on K bits. And we have that omega equals e to the I pi over 4. So any stabilizer state can be written as something just like this. Okay, yes, that's fine. So I just want to make one comment here just to sort of unpack what we have. So if you have omega to the f, this first term can go anywhere from 0 to 7. So for example, when this f of 0 is equal to 1, you might get a 1 over square root of 2, a factor sort of appearing. From this second piece, you're going to get terms that go like, these are going to be your imaginary units, I think. And this, if you have the 4 in front, when you take omega to this term, you're going to have the 4 cancel with this. So this one's going to give you your plus or minus signs. This will give you your overall phase. Imaginaries, I could be messing something up, but that's basically the structure here. And you can check that it works for various kinds of stabilizer states. So we have the following lemma, which I will not prove. So if we define f bracket as being the following, x element of z to k omega f of x, where f is a degree 2 polynomial, then we have the following. A f is equal to 0, or f is equal to 2 to the p over 2 times omega to the m, where p is some integer n, p, 2n, and m is an element of Z8. So we have either this or this, and then we have that f can be computed in order n cubed. Where is this coming from? Sorry. So yeah. So yes, the order of n cubed is coming because this calculation will eventually reduce down to something that amounts to solving or diagonalizing a matrix using Gaussian elimination. And then, so that's where the n cubed is coming from. So I won't go through the proof, but eventually you convert this problem into something in linear algebra, and then you have this. The fact that f can be equal to 0 is kind of transparent because you can have terms here that could be plus or minus 1, and because there's an even number of terms, 2 to the k in this case, you can have 0 as being, for particular functions, 0 is clearly one solution. And then you have to do some more work to show that this is the only other solution. Mm-hmm. Okay, moving on. We have one more result here. So say that you apply this projector. I have a sequence of polys that I do. This is the projector onto there, and a sequence of outcomes on those polys. This is the projector onto that eigenspace. Okay, so, and let X be a computational basis state. Then this is 1 over 2 to the T. T is the number of polys in my sequence. In fact, before stating this, I should actually make this a little bit more clear. So, because I should have mentioned this, let G be a subgroup of the Hermitian polys. Be an abelian subgroup with generators P1 to PT. Then pi is equal to 1 over 2 to the T times the product I equals 1 to T of 1 plus pi, sorry, not 1, identity, which is equal to 1 over 2 to the T sum P element of G P. Okay. So we know that this is the standard way that the projectors onto stabilizer spaces work. So now we have the lemma, which I stated a little bit prematurely. Then if I have pi acting on some computational basis state, this is equal to 1 over 2 to the T Z to T omega G of Y negative 1 Y B X transpose X plus Y. Okay, let's unpack this also. Sorry, it's not showing up particularly clear on the Zoom, I think, to some extent. This is a degree 2 polynomial. We have that X is some, so this is an element of Z to N because we have N qubits, whereas this is an element of Z to T. So this A will be a binary matrix in Z2. In order to have N come out, it needs to be T cross N. And similarly for B is also in binary matrices with T rows and N columns. So what is this sort of saying? It's saying that we have that the output after projecting this computational state, basis state, is something that looks very much, in fact, like the form of the stabilizer states that I wrote previously. And in fact, that's going to be useful. So now we want to compute the following. Now we want to compute this quantity that I mentioned. So taking psi to be, just to recall, this is u z2k and f of u z plus u. Okay, and then we will write another state, phi, in a similar way, v element of z2m. These are degree 2 polynomials, and then all the these are binary matrices with the correct dimensions for everything to work out nicely. This one, did I say what is the, so if this is k by n, so this is in zn, z2n, okay. So this one will be h of v z prime plus v phi. Same structure as before. They mirror each other. These are just two arbitrary pure states. And now we will produce this inner product. So using the two lemmas and these expansions, we have a sum over, and I will not write all the domains of these summations for everything because we previously wrote it down. Sum over u, v, and y. So this is omega of g of u, no, g of y, sorry. That's g of y plus h of v minus f of u, because this is now a bra, minus f of u. And then coming from the projection part, we have negative 1 to the y e x transpose, and the inner product of these two, which I will write like this, z plus u capital psi z prime plus z prime plus, now we have a term like this, plus v phi plus ya. So we want to compute precisely this. Of course, these are computational basis states, by the way. Or sorry, stabilizer states. Okay, so this is, sorry, no, these are, in fact, yes, these are computational basis states. Okay, so these can be either 0 or 1. So how do we enforce precisely this condition? When are these 0 or 1? Right, because these are just two bit strings. So, and when the bit strings are different, then this inner product is precisely 0. So we have the following condition, that z, so we only get non-zero terms when you have that the following bit strings are equal, plus u psi equals z prime. I'm just rewriting what's inside of here, plus phi plus ya. So these need to be equal for you to have a non-vanishing term here. So these are terms are non-zero if and only if. And then how can we write this down? Z plus u we will see that this will work out to be correct. So to the 2n, introduce an additional variable, x element of z2n, and you write down -1 x times, and it will just be a sum of all of these terms. Z plus z prime plus u psi plus v phi plus y a. And now how does this help us? Suppose that these two are equal. When these two are equal, then this sum will be equal. So let me write down the cases. So if, let's call this, let's see, what can I call this? Alpha and alpha prime. These are two bit strings, alpha and alpha prime. If alpha equals to alpha prime, then we have that this function here, well, if this is 0, then this is -1 to the 0, and you just have a sum over +1. There's n, there's 2 to the n possible bit strings, and then you just have that the outcome of this is 1, like you would want. If alpha not equal to alpha prime, what happens then? If alpha is not equal to alpha prime, then you have that there's an even number of terms here, 2 to the n, and you're summing over. So if I fix the value of this to be some bit string, there will always be an even number of positives and negatives, or sorry, zeros and ones. Sorry, I don't really have time to show it, but it's not hard to sort of convince yourself that you will either just have it be 0 or 1, and then since there's an even number of terms, you have that this goes to 0, so which is precisely what we want. So actually, I will keep this and I will get rid of this part, more or less. Okay. And so we can finally write down psi projector as being equal to 1 over 2 to the n plus t. One of these is coming from the action of this projection, and then another one is coming from the identity that I wrote down before. And I have a sum over u, v, x, and y. These are all bit strings. Omega of f of u, v, x, and y. This is a degree 2 polynomial over, you have how many different variables here. You have to sort of sum over what each of the variables here is. And this is equal to, because now this is in the form, we had the lemma before, that we know precisely how to compute this. This is 1 over 2n plus t f. Okay, where we have that f of u, v, x, y. So what did this function look like? G of y plus h of v minus, some of this I already wrote down, f of u plus 4 times, where's the 4 coming from? Yes, when I have this -1 here, -1 is omega to the 4th. So I have 4 times whatever was coming next to these terms. So 4 times y a x transpose plus 4 times x z. Yeah, so I think that this is the alpha plus alpha prime term that I wrote down before. So I won't repeat it. So we have the following. By that lemma, we can compute psi pi phi in. Okay, and I think I misspoke before. These are stabilizer states. Sorry, I think at some point I might have said these are arbitrary kets. That's not true. This is an expansion of just stabilizer states. And so what we just computed was this inner product, this probability for the inner product between stabilizer states. So now the direction that we're going to go in is to expand something in terms of the stabilizer rank. You will take an arbitrary ket or maybe like a magic state. It has a particular stabilizer rank. And then each of the terms in that stabilizer rank can be computed amount to a function to a term like this, which we can compute in n cubed steps. So yes, in fact, let me think if I can just, because we're coming on towards the end. Okay, so let me think. Okay, so let's go like this. So what's the simulation algorithm look like? It's the following. So we use a poly-based computation. So now what am I describing? I'm describing the classical simulation algorithm. This was just a preliminary result, and now we're going to use the stabilizer rank to actually simulate quantum circuits. And so this is how we're going to do the classical simulation. Use a poly-based computation. Sorry, this is not big enough. Given a step t steps and outcomes of previous polys sigma 1 to sigma t. We want to, so given this, we want to return the probability that we obtain this bit string, sigma 1. I guess it's not a bit string, these outcomes. So just as a side note, this algorithm, given these, it returns this set of probabilities. If we run the algorithm twice, but on one less set of, so for example, we can also compute probability of sigma 1 given, sorry, sigma t, given sigma 1, sigma t minus 1, because we have this law of probability, sigma 1, sigma t over probability of sigma 1, sigma t minus 1. Basically, if we run this algorithm twice with up to t minus 1 on the second time, we can also get conditional probabilities as well. So now let's figure out how to actually get the runtime that I promised. Okay, I think that this is fine. And it goes as follows. So let's consider how many terms? K tensor factors. Sorry. K equals alpha equals 1 to the stabilizer rank chi. I guess chi k if we want to be sticky about it. These are stabilizer states. Okay, so we have chi terms here, and let's consider the fact that we have the following situation. We have that n is equal to k times m. So the number of qubits total is equal to k, what I started with, times some integer m. And you'll see why we're doing this. So we'll have the following. H to the m is equal to, now the notation here is probably not perfect, so I'll have to explain what I'm doing. A equals 1 to chi to the m, Ca by A. Okay, so a couple of things here. I'm taking m factors of this. So I'm going to have m copies of these coefficients. So Ca is equal to, or maybe first, A is enumerating over all the possible terms in the stabilizer rank. So it'll be alpha 1 to alpha alpha m. Sorry, this is not what I... yes, okay. So what do I mean by this? So alpha 1 is the first set of coefficients. It's indexing the first set of coefficients from the first tensor factor of k h's, and then so on and so forth. Like I said, the notation is not perfect here. Ca are m copies or m products, C alpha 1 all the way to C alpha m. But you see what we're trying to do. We're just taking m factors of this. So you're going to have m products of these. And then you're also going to have how many terms? Chi to the m terms. And then also you're going to have these stabilizer states, which are m tensor factors, which are again then stabilizer states. So it's kind of intuitive, but the notation is not great in this case. Okay, something like this. So now we want to compute the following. So now that we've written all of this down, what we want is the following. So we have this projector, which will be defined like before. You have sorry, I don't need this. Okay, same as before. And then we compute the following. Sigma 1 to sigma t is equal to h tensor n precisely this, which is going to be a sum over all of these terms. You have a, b. So the same terms that we have here, but now you have to square them, the number of them. So this is going to be from 1 to chi this was chi to the m, so each of these is chi to the m. So a total of how many, but this is a sum over a and b, so there will be chi to the 2m terms altogether. C A star CB phi A phi B. So there's chi to the 2m terms altogether, and each of these can be computed in order of n cubed. So this is just the quantity that we wrote down before. So this is precisely, you have a runtime of order chi to the 2m times poly n. So this is precisely the runtime. Now let's just do one more thing to show how you can get a good number out of this. You actually have to go ahead and compute the stabilizer rank chi for some initial chi to the k. So now the last part of this, find chi k for some k. Okay, and it turns out that this is a little bit of hard work. So we have maybe the following table, n chi n is less than or equal to. So when n equals 2, we could also do for n equals 1, we know that it's 2. We know it's exactly 2, but it's less than or equal to 2 for sure. So with 2, we also know that it's 2. For 3, it turns out to be 3. For 4, it turns out to be 4. For 5, it turns out to be 6. And the one that we end up wanting is chi 6 is equal to 7. So I will not write down exactly this expression, but what does that give us? So if we have chi 6 is equal to 7, then we run this, then we take this expression and we have something like order of, chi is, this is 7. One moment here. Okay, yes. So then you have n over, yes, chi to the 2m. What is m? M is 2 over k. Sorry, this is where I'm messing up. This is n over, and in this case, k is 6 times poly n. So this will be, this is n over 3, 7 to the n over 3. You change the base of this exponential, you get that this is something like order of 2 to the alpha n poly n. And when you change this exponent, you have that alpha is like 0.94. Yes, so in general, it's a hard problem to figure out what these stabilizer rank decompositions are. You can try and go higher order, and I don't know what the state of the art is. Maybe some people have improved on this, but I think that people have gone in opposite directions. Instead of going for this exact stabilizer rank, you can go for approximate stabilizer rank. And so I think that that will be the next paper that we talk about on the, it's either we will talk about that or quasi-probabilities. So, any questions?
No.
No questions. Okay, very good. Well, happy World Quantum Day one more time. There will be no seminar next week because it's holiday here in Turkey. Okay, so I'll see you guys in 2 weeks.